We'll go over all 10 of these. We'll knock it out. All right, so we're going to go over the first, well, all 10 questions of this 12.3 lesson. This is Unit 8, Day 3. So you're going to want to open that up from Sapling. And I'll back it up with some information that was in the lesson, so that way we can see what's going on with that, okay? So if you want me to read the questions, I can read them, just to kind of process it a little bit. Two introductory statistics students, John and Diane, little ditty about John and Diane, are discussing the validity of a linear model to fit some data that John collected. It doesn't quite jive with the whole song, but it's fine. John tells Diane that he randomly surveyed 100 students at his university and asked each student how much they slept last night in hours and how happy they feel today on a scale of 1 to 100. Diane tells John that she is not sure if a linear model is appropriate, because people talk like this normally all the time, right? They're like, hey, should I put a linear model for our sleep? Yeah, why not? John shows Diane the scatter plot of this data with the least squares regression line and the corresponding residual plot. Welcome, Sarah. We're going over the sapling. So if you want to open that up, we're going to go over these questions, okay? So here's what we got. Now you might remember this from Unit 2, which had the 2 variable data. And if I were to design the textbook, I probably would put this with that unit. It just seems like it would flow a little bit better, but I'm not a textbook designer. So here we go. John would like to use these data to conduct inference about the slope of the true regression line. So first thing is, if you look at, if you remember anything about residuals and stuff like that, is if you have a residual plot. So a residual plot is when they have like a flat line and we're looking for a random scatter that kind of helps you determine, hey, it looks like a linear model might be appropriate. And of course, here is the data here, and you can see it's a positive linear relationship. Is it strong? Doesn't look like it's terribly strong, but it does have a positive linear relationship, okay? So let's look at what the question's asking. Do these data yield a valid model for performing inference about the true relationship between hours of sleep and happiness? Well, I would look at that data and say yes, they do, because a linear model seems appropriate. There's no pattern in the residuals, but we got to understand why that is, okay? So I think the linear model is valid. But there's a couple different ones that say the linear model is appropriate, right? The linear model is appropriate for these data because the data are paired and quantitative, and his linear model is appropriate because the conditions are met. Well, you could have data that's paired and quantitative and still not have a linear model. I mean, you could make a curved model and have paired and quantitative data. Does that make sense? It could be exponential or quadratic. So that's not really the reason. The reason is that the linear model says the conditions are met. And if you watch the video or followed along with that slide, I pulled up those conditions because it's a lot. If anybody had Miss Liner from Math 2, maybe you remember LINE, you could kind of help that remember. But there's a few different things that might ring a bell, like independent, normal, and random, right? Those we're used to, but there's other ones too, like the data has to be roughly linear, and there's something called equal standard deviations. So I'll go over that in a second, because we're going to hit some more conditions. Actually, let me go over those real quick. So linear just means, hey, is the residual plot are randomly scattered, or does the line itself look particularly linear? If so, a good fit would be a linear model. If not, then that wouldn't be a linear model. So we've met the linear condition. Independent, typically the 10% if you're sampling from all replacements. So that's not really a situation here. Now the normal is talking about the distribution of the residuals. So usually you'll look at the residuals, and you're never going to have to make this distribution. They'll be in like a histogram or something. And if there's no super strong skewness or outliers, that means it's normal. And then equal There's heteroscedastic, which is just a fancy word for saying it kind of expands as it grows. So if a residual plot like expands or kind of looks like a funnel shape and gets bigger outside, that's not a good sign. And finally, the random is, you know, the same random people were randomly selected or sampled from. So if you look at the data in there, everything kind of lines up, and it tells you the scatter plot is, there's no pattern in the residual plot. It looks like it's a linear model. All the conditions are met. So we're going to go with that one there. So let's look at the next one. How well does the number of beers a person drinks, don't drink beer, predicts his or her blood alcohol content? 16 volunteers aged 21 or older with an initial BAC of 0 took part in a study to find out. Each volunteer drank a randomly assigned number of cans of beer. Wow, so somebody was randomly assigned 9 beers. I want to be around that guy. So look at that. 30 minutes later, a police officer measured their BAC. Oh God, this looks like a terrible study. Well, I want to see this. At least square, I know it was made up, but like I really want to see this played out. At least squares regression analysis was performed on the data using X number of beers and blood alcohol content. Given is a residual plot and a histogram of the residuals. All right, let me get over the problem and let's look at the question. Explain how the graphs shown verify that the normal condition for preferring inference about the slope is or is not met. So the normal condition is basically saying it's not related with the residual plot. It's more along the lines of, if you were to make a histogram of the residuals, would there be any strong skewness or outliers? And so that's what we're looking for. Hello, Christina. We're going over the sapling assignment. So if you want to pull up the Unit 8 day 3 assignment, that's what we're on right now. So if you look at the residuals just as a histogram, yes, there is one that's kind of peaked here and it's a little bit skewed, but it's not super skewed. Really aren't any outliers. So the normal condition would be met because of that. Not the residual plot. Okay, that's not telling you the normal condition. It's actual the histogram of the residuals. So which one is that? Normal condition meant there are no leftover curved. No, it's not the curved. The leftover curved patterns here, that would be like if the residual plot tells you it's linear or not. So that's not the situation. The normal condition is met because the residual plot shows a random scatter. That's again linear, not the normal condition. The normal condition is not met. That's not true. The normal condition is met because the residual plot has a number of points which could be outliers. Again, no. It's the normal condition because the histogram of the residuals doesn't have any strong skewness. So don't look at a residual plot to determine normal condition. Look at the actual graph of residuals, like a histogram or dot plot even would be better than residual plot, okay? That's what you want for that. Question 3 is actually not anything to do with what we are in this unit. This is more along the lines of, hey, do you remember how to plug in numbers? So if you look at this question here, using the daily high and low temperatures at Chicago's O'Hare International Airport. I've been there a couple times, it's crazy. A meteorologist made a scatter plot relating y equals high temperature to x equals low temperature, both in degrees Fahrenheit. After verifying the conditions for the regression model were met, the meteorologist calculated the equation of the population. And here's the equation. So it's the mean of the y equals 16.6 plus 1.02x. So notice they didn't put y hat. They said the goal is we're trying to estimate that. Okay, so we say what is the actual mean of the y? We're trying to figure that out. This standard deviation is the standard deviation of the residuals. So this 1.02 is the slope. Here's your y-intercept. What's the average high temperature on days when the low temperature is 40 degrees Fahrenheit? Well, again, x is the low temperature. So this problem, don't make any more than you have to out of it. we're just plugging in 40, right? It's just going to be 16.6 plus 1.02 times 40, because if you plug in 40, you're going to get whatever the predicted average Y temperature is. Okay, so plug in 40. There's only one place that even shows you're plugging it in correctly to begin with, right? So if you do that, you might want to double check, but you should get 57.4 when you plug in 40. So that one was probably the least amount of thinking involved. This is just plugging in a number. Any questions on that one? Okay, it says I'm correct. Oh, I didn't click next question. I promise you, when you take the AP exam, most of your data for slope and intercepts are probably going to be in this form. So a lot of it's done for you. We just have to know how to pick it apart and analyze the numbers, okay? So focus on that table here. We'll read through the problem so we understand the context behind it. Here is one way in which nature regulates the size of animal populations. Big animals eat small animals. High population density attracts predators, which remove a higher proportion of the population than when the density of prey is low. One study looked at kelp perch and their common predator, the kelp bass. On each of 4 occasions, the researcher set up 4 large circular pens on sandy ocean bottoms off the coast of Southern California. He randomly assigned young perch to 1 to 4 pens so that one pen had 10 perch, 1 pen had 20 perch, 1 pen had 40 perch, and the final pen had 60 perch. And he dropped the nets according to pens, allowing bass to swarm in and counting the number of perch killed after 2 hours. That sounds fun. These are just fun experiments, making people drink and killing animals. Man. A regression analysis was performed on the 16 data points using X equals number of perch in pen and Y the proportion of perch killed. Here's the computer output. Now, we likely didn't need to read through that to answer this question, but anyway, let's look at the computer output. Given the standard error of the slope, SEB, interpret this value. So first of all, let me tell you where the standard error of the slope is. Let me review this computer output. The top number here, where it says constant, that's going to be your y-intercept. So this number here, we call that B. Actually, it's y hat equals a plus bx. Excuse me, I spoke too soon. The A value is usually your y-intercept in stats, right? I got back into algebra here mode. So that's A. And then your x value, your slope value, that B, that's going to be this number here. So when it says coefficient, those are your y-intercept, those are your slope. Now, if you go over here, there are formulas for standard error, but you're not probably ever going to use them or need to calculate them because they're usually going to be right here. Standard error, I know it says standard deviation, but that is standard error, okay? And that's going to be 0.09 for the y-intercept and 0.002 for the slope. So when it says SEB, since that B is the slope, that is the standard error of the slope. So now that we know it, it's going to be this number here. We can interpret the value. So we can eliminate any problems that don't have that number from the beginning. Okay, so it's going to be 0.002, 0.002456. I'm writing that down because this is about to disappear as I scroll down. So let's look at the ones that have that number, and then we can talk about how to interpret it. So we're going to get rid of this one and this first one here. So we have 3 values that give you that same number. Now let's go through and see what happens. So the standard error of the slope is this number, and we have 3 scenarios. If we repeat, the first one is if we repeated the random assignment many times, the number of perch will typically vary about this much from the predicted slope of 0.002456. Okay, so the next one is if we repeated random assignment many times, the slope of the sample regression line would typically vary by about this much from the slope of the true regression line for predicting proportion of perch killed from number of perch. Let me talk about this really quick first. This one's wrong. And the reason it's wrong is because of the table. Like, look at the table. The slope here is 0.008569. It says it varies from the predicted slope of 0.002456. Well, that's not even the right predicted slope. So we just have incorrect numbers there, okay? For this third one, it seems plausible, but let's look at the last one here. The slope of the regression line is this number. No, that is not the slope. Oh, hold on. That number from the slope of the true regression line for predicting proportion of perch killed from number of perch. Well, that's awkwardly worded. It's typically that far away from the slope. It's not that far away from the slope. It's typically, if we were to repeat this, just like standard deviation, like typically each point is this many units away from the mean, right? In this case, think of the predicted slope as the mean. And if we were to do this sampling many, many times, that slope would vary by whatever the standard deviation or the standard error of that slope is. So the wording, if we repeated this random assignment many times, the slope of the sample regression line would typically vary about this much from the slope of the true regression line for predicting proportion of perch killed from number of perch. So it's all about the wording. And these, a lot of times these are worded very similarly, so you have to really pick it apart. Any questions on that one? All right, here's the same scenario. It wants to know what is the estimate for this standard deviation. Now, I want to just warn you that, again, in this table, it usually says standard error, not standard deviation. And even if it says STDEV, these numbers are the standard error. This is the standard error of the y-intercept, and this is the standard error of the slope. And remember, standard errors account for sample size. And I'm not even going to worry about the formula for that because, again, we're going to be given those numbers. But when it asks for this, the estimate of the standard deviation, they're talking about the standard deviation of the residuals. That's this here. That's this number, okay? This is the standard deviation of the residuals. But again, all these are statistics. These are estimates, right? We don't actually know the population standard deviation of the residuals. We'll never know that, but this is an estimate of that. So we have to find the one that has that number, 0.00 or 0.1886. And we'll go down here and we'll find that there's only one that even has that, okay? So the estimate for the standard deviation is 0.1886. The actual proportion of perch killed typically varies by this much from the proportion with the least squares regression line using the number of perch. In other words, standard deviation of the residuals. So it's going to be this one here. Will you ever have to interpret that? You probably won't even have to deal with that on the exam. We're really more focused on slope, like how good of a fit is the slope in our sample. So most of our solutions will revolve around that. So that takes us to this. A lot of times they'll use this beta to represent the true slope, because remember the formula that we learned in chapter 3 was y hat equals a plus bx. But beta, anytime you do a regression, remember this is an estimate, right? You don't ever have all the data. So this estimates the parameter, which is the true slope. So what we get here, even though it's lowercase b, it's estimating the true slope. So we want the estimate to be whatever our sample is, right? So we can eliminate these three. So let's look at the wording of these two. For each increase of one perch, the proportion killed will increase by that much. Versus for each increase of one perch, the average proportion killed increases by that much. Well, what's a better wording? I mean, it really just comes down to that. Is it the proportion killed or the average proportion killed or the typical? We can go back to the wording from the previous time we studied this. So I know it's been a long time since we've done two variables, but if for like predicted y values, we could say for the slope means when I increase x once, the typical y value, the average y value will increase by this much. It's the same thing for this. You want to use language that is a little bit more, I guess, vague, if that makes sense. So we'd say like the average proportion killed increases by that. And that's the one thing that kind of sucks about statistics is a lot of times the language is so complex, you know, it makes you get wrong answers in multiple choice. That's why I really don't like multiple choice questions in statistics. And I would focus more on free response if we were in person, but it's just hard to coordinate free responses with online learning right now. Because I think if you did more of those, you would write enough to kind of get the language down a little bit better. So I feel you here. All right, let's look at this number 7. Same question, what is the estimate for A? Again, this is the, what we call like the lowercase a, like the y-intercept A, but it estimates the true A. And again, they're throwing this alpha out there like, hey, I can just casually put alpha for alpha level on a test or just y-intercept. And I get it, it's kind of confusing with this, but just remember that typically Greek symbols mean like the parameter, whereas just lowercase symbols typically mean like an estimate or whatever. So this is your estimate for A, 0.12049. And the nice thing about this one is we only have one to work with, right? If a pen has 0 perch, the proportion killed will be that on average. See how they threw on average again. So remember the y-intercept is when x is 0. So if x is 0, then typically then you would see this number here for the y-intercept. So we don't have to worry about a process of elimination on that one because it took care of itself. All right, we're going to go over how to get a confidence interval. For this, you will need your calculator. So let me pull mine up. Notice how we didn't have to enter any data into L1 and L2. If we had to do that and then do all this regression stuff, it would take you all class to do one problem. And so, you know, you're never going to really have a lot of handwork to do for these. And also, I'm not doing free response on these questions here. We're just going to stick with multiple choice for the time being so we can see how to analyze those. So this question, a tire manufacturer compared 2 methods for estimating tire wear. The first method used the amount of weight lost by a tire. The second method used an amount of wear in the grooves of the tire. A random sample of 16 tires was obtained. Both methods were used to estimate the total distance traveled by each tire. The given scatter plot displays the 2 estimates in thousands of miles for each tire. So the weight method versus the groove method. Also given is some computer output for a least squares regression analysis. So all the work's been done for us. We could write if we wanted to write the formula, we could say y hat equals A, so 1.351 plus 0.79021x. So that's your formula just from these numbers. And this represents the standard deviation of residuals. Here's your R squared, your standard error. See how it says SE here? So this is what it is actually called, the standard error of the y-intercept, standard error of the slope. And then here are some other numbers, T and P. So if you were to run a test, you would get a T value, like a T test statistic, and a P value. Typically, we do test on the slope, not the y-intercept. So you're not likely to ever use these 2 numbers, but you will probably use these numbers. So let's first talk about the confidence interval. How do we get a confidence interval? The formula for confidence interval is the statistic plus or minus our critical value. And I'll explain how to get that here, times the standard error. Well, guys, we're given the standard error, and we're given the statistic. We only have to figure out what the critical value is. So the statistic is, if it's talking about slope, our statistic is B. That's going to be 0.79. Now, I don't know the critical value, but I know the standard error is right next to it. So that standard error is 0.07. So it's just a matter of what number gets multiplied with that. And so if you look at these things, we're going to eliminate these two right here and that one at the top. It's really is, how do I get my critical value? And yeah, these are slope, because it deals with numbers, quantitative, it's averages, it uses t-distributions, okay? So we can get critical values using your t-distributions by going to inverse t. Or we could look at table B, but again, I'm not a huge fan of table B, so I'd prefer to use inverse t. But I do want to caution you, because it's going to ask you for degree of freedom. And prior to this unit, we have typically had a degree of freedom, the number of people in the sample or number of the objects minus 1. When you're dealing with scatter plots, 2 variables, we actually have to subtract 2 because there are 2 variables. So anytime it's for scatter plots regression, you're going to take the number in the sample and minus 2. Now, I don't recall if it said what the number in the sample was, so I'm going to have to go back up there and find it. But that's what we're going to do. And remember, when we're doing inverse t, you want to take that for the area. You want to take your confidence level, so 0.99, and average that with 1. And so you add 1 and divide by 2 when you put that in. So let me put that in here. Can somebody find where the sample size was? How many tires were used? 1/6? Okay. 6D or 16? 16? Okay, I guess you could just count the number of dots here too. So y'all can verify, but the N is going to be 16. So your degree of freedom will be actually 14, not 15. So let's plug that into here. Second vars, inverse t. Let me erase some of this stuff here real quick. And your area, remember, is averaged with 1. So 0.99 plus 1 divided by 2. Your degree of freedom will be 14, not 15. And that'll be your critical value. So it's 2.976. So I guess it's going to be this one here. Any questions on that? All right. Now this one's pretty similar, so if you want to try this one and see if you can kind of follow the same procedure we did on the previous problem, take a minute to do that if you haven't done it yet. Based on the slope and the standard error, you can probably narrow it down to get rid of a couple of the answer choices that way. Remember, we're only looking at this line here. These are your important numbers. Estimate of the slope and the standard error of that estimate. So if you've gotten rid of those two as your possible ones, then we're on a good start. But now we got to figure out the appropriate number that is going to be the critical value, okay? Using 90% confidence, and we got to figure out how many people were in the sample, or perched were in the sample. Oh, 16. Oh, it's the same problem. We able to get it? Okay. All right, I'll go ahead and put it on my calculator. Y'all, were you able to figure it out? Let's see. I'm just going to replace that with 0.90 and see what we get. 1.76. So looks like it's going to be the middle one for me. I think yours are all scrambled up, so it should be 1.76 for that. Any questions on that? All right, and let's finish it up. So how do you do a test on this? Well, let me explain how the test works first, because I want to show you how to actually get a p-value of this thing here. So when you do a test, you're just trying to see, is there a reason to conclude that the slope is less than than 0 or something like that? It's, again, these are kind of weird, but basically what you're going to do is you're going to look at your slope. If I were to do a null hypothesis, I would just say, hey, there's no relationship. So the null would just be the slope is 0. And then since my sample slope was negative, my alternative would just be slope is less than 0, right? That's typically how that works, right? Your sample slope, all right, I got a negative relationship. Looks like there's something to conclude that there is a slope that's less than 0. So there's some sort of relationship going on. And then you run a test and you get it spits out all these numbers, right? It gives you a test statistic, which is negative 4.163. I can tell you how that number can be gotten, okay? That t, and y'all can do this, you can verify it. That's the easiest thing to get on this table, because if you take your slope, a test statistic is your average, your sample minus 0, there's no difference, divided by the standard error. Well, we have these two numbers here. So you can actually get that t and test it out. Type in negative, put the slope on top, so negative 0.0483, and divide by 0.0116. That's your t. That's negative 4.163. Now, where does the p-value come from? Notice it's 0.0003. That's going to be TCDF. All right, we're not running a test in your calculator here. You're just going to do TCDF. And what it's going to look like is your lower, since it's going less than 0, is going to be negative infinity. Your upper will be the negative 4.163. And then your degree of freedom, since it took 30 volunteers, the degree of freedom should be n minus 2, so it should be 28. So I'll show you how to get that, that p-value, even though it's already given to you. TCDF. And if it were a positive test statistic, you would start with that and go to infinity, okay? So negative 4.163. Degree of freedom, we'll put 28, since there are 30 people. And it says 0.0003. Mine says, oh, was this a two-sided test? If it was a two-sided test, I would just double it by 2. And that would round to 0.0003. I can't tell, let's see. They wanted to know if listening to music at a louder volume negatively impacts test performance. No, it should be a one-sided test if it's negative. So that p-value should be 0.0001, but I'm just going to go ahead and go with what's here. Let me clear this out for a second. Because the p-value of 0.00015 is less than alpha, we reject the null. Well, we want to reject the null if it's less than alpha, right? So first thing is we're going to look for the ones that reject the null. So we can click out the fail to reject. It's smaller. But now we have 3 of them that have different p-values, right? We have a p-value that is 0.0015. Ah, so I did get 0.00015 in my calculator, didn't I? That was for the one-sided test. Because the p-value of 0.00015 is less than alpha, we reject the null. There is convincing evidence of no linear relationship relating the Y performance of the 10-question math test to X, the volume of the music for students like these. Option D, because that p-value of 0.00015 is less than alpha, we reject the null. There's convincing evidence of a negative linear relationship relating Y equals the performance of the 10-question math test to X equals the volume of music for students like these. And the last one, because the p-value of 0.0003 is less than alpha, there is convincing evidence of a negative linear relationship relating Y equals the performance of the 10 questions. Well, on this problem here, there is convincing evidence of a negative linear relationship because it's negative. And if you look up that p-value, even though it said 0.0003, that p-value most likely as a computer output is a two-sided test. But if it's a one-sided test as a negative, we would cut that in half. So based off of that information, you would have to pick this one, I hope. There is convincing evidence of a negative linear relationship in this case. Whereas here, if it's 0.0003, that would be a convincing evidence of just no linear relationship. So I'm going to click the second to last one here. And it said I'm right. So because in the way it's worded, it's a one-sided test. So you'd have to cut that p-value in half. That's confusing on that one, but that is the kind of the way it gets worked out here. So there it is. There is your sapling. It's completed. Should you have not done it prior to, or you did it and you just wanted to go through it again. The only thing that I have put out there for you is the practice test on sapling. So you might notice it says Chapter 12 practice test. And what I'll do is I'm going to make an assessment. It's not going to be long. It's going to be 11 or 10 questions on when you come back on Tuesday. And I will certainly spend some time going over questions on that practice test, even making a video for it. But I promise you that assessment will be so much similar, very similar to that practice test. So you can kind of look on those questions and get a rough idea of it. So that way you're on the right track to get a good grade on it, okay? So I'm not going to make it too challenging just because we've only done a few days into it and it's right before spring break. But my goal was to try to wrap it up before spring break so we can really get into review. So I am cutting a few corners on this unit, okay? So where does that leave us? Well, if you click on the assignment here, you'll have the lessons, you'll have the very last thing on Unit 8. All I have posted on the review is to click on that sapling and do that Unit Chapter 12 practice test. Since I have not posted any solutions or a video, just start working through it the best you can. My suggestion is go through it on your own. Once I submit, solutions, if you want to go back and retry it, I can open it up again so you can do it again if you'd like. I think I have that power. If not, I'll figure something out. And I'll have those solutions up there as soon as I can, okay? But you can do that asynchronously. It's going to cover chi-squared and the regression stuff. And the level of those doesn't seem to be super high level. The practice test also aligns, if you're interested, in your textbook. If you look at page, I got to find it real quick. 846 of your textbook, you can see those questions on paper. So if you want to read them there first and try it before you get into sapling, that way, you get a couple attempts at it. So it's page 846 of your textbook. And the textbook does give answers. I know a lot of you don't crack that textbook open, but it does give answers in the back, and all the review and practice test solutions are back there. It's only going to give you the letter of the correct answer. It won't provide an explanation, but I'll put that in video form or work it out or something like that when I get a chance to upload that for y'all. Sound good? One last thing before you go. I know that on Wednesday we had a short class and I had started a quizzes. Y'all didn't get a chance to finish it. I had some issues with the link. So if you were trying to do that, I think that link went away. Oh, hold on a second. It would have been on the 12.3 lesson. So I relinked it, and I made it so that the timer was not there because I think the timer put on there, and I did not mean to have the questions timed. So if you want some more chi-squared review that are kind of similar to AP problems, again, I'm not making it mandatory, but if you just need some extra chi-squared review, you can go to that quizzes from Wednesday's lesson and just go at your own pace. And hopefully you'll get some explanations from those. But that's it. I'm going to let you guys go and work on the Chapter 12 practice test asynchronously. I hope you have a good weekend, and I will see you on Tuesday.
Bye.
See ya.
Bye, Mr. Weiser. Have a great weekend.
You too. Yeah, you can go real long if you want. No, did you make a pass or not? I got you. I'm already at it. You can go. I'll get you on here. Yep. I'm just kidding. I'm not saying go out forever, but take your time. Which one are you going to? Okay. All right. What were you thinking you would work on right now? Okay. Did you want to go over any of it? Or were you just kind of starting it up?
I just.
Okay.
It's the cheese.
Okay.
I was cheese.
It looks like cheap. Well, if you come across anything, you will just use me as I'm here. I did go over the very first video lesson. Is it the unit 8 day 1 or day 2? One of them has like 10 questions, one has like 18. Day 1? Okay.
I did.
Gotcha. That one, you can ask me for help from here, but if you don't get all your questions answered, I think I did put a video going over all of those ones.
Yeah, I'm in AP biology too, so like, we did this in the beginning of the year, and it didn't make much sense. And we did it here, and we did it in biology again. Now it's like, hard to get it.
Too bad we can't like coordinate that, you know, to kind of be done at the same time. I mean, we could, just we'd have to figure it out. Chi-squared. See, this last chapter, in my mind, we don't do like regression anywhere else but chapter 3. So I almost want to pull that in after we do all the hypothesis testing, and show all the regression stuff at once, and then do that last section of 12, because I think it would make more sense. And as far as the chi-squared stuff goes, since it deals with like distributions and proportions, it almost would fit better with the unit 1 stuff. Like the very first chapter, it has all the how to make a graph and stuff like that. But I don't know. I have to redo the whole book, and I ain't about to do that.